So, welcome to all. Myself Dipti Ranjan Patnaik. I am working as assistant professor in GL Baza Institute of Technology and Management, Greater Noida. Today we will see the digital modulation technique part 2, that is we will see the frequency shift keying. So, in the last lecture we have taught about ASK, amplitude shift keying, and what is the definition of amplitude shift keying? That is nothing but the amplitude of the carrier signal is changing or shifting with respect to the your message bits. Okay. And we have calculated the we have already seen about the binary ASK transmitter and binary ASK receiver. Then we have calculated the probability of error if I am sending the bit 1 and I am getting 0, if I am sending bit 0 at the transmitter and I am getting bit 1 at the receiver, what is the probability of error what is the probability of error to get like this type of error. So, we have seen we have considered Gaussian waves for this analysis and we got some probability of error. Now, we will see second modulation technique, that is your frequency shift keying. So, nothing but it is nothing but the frequency of the carrier signal varies with respect to amplitude of the message signal. So, your frequency of the carrier signal varies with respect to your amplitude of the message signal, and during that phase and amplitude of the carrier signal are constant. Okay. So, your baseband signal, that is modulating signal, message signal, is nothing but your, this is the message signal, this is 1 0 1, and your sinusoidal wave carrier, that is continuous continuous wave, that is carrier signal, sine wave carrier signal. So, for logic 1 this is only the high frequency, and for logic 0 it would be low frequency, and for logic 1 again this is for high frequency. You can see that your amplitude of the carrier amplitude is constant, same constant, and your phase is also constant, it is not varying, because you can see this phase is continuously, this is changing like this. Okay. This is the changing, but it is not changing like this. Okay. So, your phase and amplitude of the carrier signal are constant. Now, in the ASK system, that is binary ASK system, herein also for symbol 1 and 0, if symbol 1 and 0 are transmitted as S1t, that is symbol 1 is root 2 EB by TB cos 2 pi F1t, that is some frequency for symbol 1, and for S2t root 2 EB by TB cos 2 pi F2t for symbol 0. In case of amplitude shift keying, it was for symbol 1 it was some S1t was there, but for S2t it was the symbol as amplitude was 0, that is why your S2t was your directly 0, but here S2t is there, but with different frequency, that is F2. Okay. And your T, that the T is lies between 0 and your bit period. So, the basis function are given by we have already know the in the last lecture also. For this we have to know the basis function. So, for symbol 1 S1t, the basis function is your phi 1t, that is nothing but root 2 by TB cos 2 pi F1t, and for phi 2t, that is root 2 by TB cos 2 pi F2t. Okay. So, therefore, FSK is characterized by two dimensional signal space with two message points, but in case of ASK it was only one dimensional signal with two message points. It was one dimensional in ASK, it was one dimensional, that is your 1 is 0, 1 is root EB, but in case of FSK it is two dimensional, and this is your nothing but your phi 1 t, but in the case FSK we will see in the very next slide that your phi 1 t two dimensional, this is your phi 2 t. So, you can see the FSK is characterized by two dimensional signal space with two meshes points, that is S1t is nothing but root EB phi 1t. We have calculated, we have also calculated seen in the ASK. So, S1t I can write this as a root EB multiplied by root 2 by TB cos 2 pi F1t equal to nothing but root EB, this is your 2 by TB cos phi 1t, this is nothing but your phi 1 t. Similarly, for S2t I can write root EB I will take outside, and 2 by TB cos 2 pi FTT is nothing but your phi 2t, and I will get S1t as root EB phi 1t and S2t as root EB phi 2t. So, again the symbol period lies between 0 to bit period. So, the coordinate points are given by I got S1t and S2t. I want coordinate points where that points exactly located. So, S11 is nothing but the integration 0 to TB, that 1 is nothing but your message point S1t, okay, that is your message point S1t multiplied by corresponding basis function, that corresponding basis function is your phi 1t, that is why this 1 and 1 it is written like S11. So, 0 to TB your S1t is nothing but your this one, that is root 2 EB by TB cos 2 pi F1t multiplied by again phi 1t, that is root 2 by TB cos 2 pi F1t dt. So, after multiplying this I will get again same I have already calculated in ASK, that I will get only root EB. Similarly, S12, so that S12 is nothing but your S1 point is S1 message point, and phi 2 your what phi 2 is your nothing but your basis function. So, S1t multiplied phi 2 t dt. So, again S1t is nothing but your root 2 EB t divided TB cos 2 pi F1t, and phi 2t is nothing but 2 by TB cos 2 pi F2t dt. Now, the message point 1 is given by your message point 1 is given by the coordinate point is your root EB 0, that is S1 is nothing but S11 and S12. So, S11 is your root EB and S12 is equal to your 0. Similarly, I can find out for S2 I can find out S21, that is S21 is nothing but the your S2t your message point, and phi 1t is your basis function, and after multiplying this S2t, what will be S2t your okay, your S2t would be, I know that the 2 and 1, this would be multiplication is your 0, and S22, that is your S2t and phi 2t, and following this we will get this, following this S2t we will get root EB. So, the message point 2 is given by S2 equal to your, this is nothing but S21, this is your S22. So, S21 is 0 and S22 is equal to root EB. I have not calculated this one because I have calculated the S12 and S11. In the following the same method, we can calculate the S21 as 0 and S22 as root EB. So, now we will move to signal space diagram. In ASK it was like this is 0 point, this is root 2 EB, okay, and this was the threshold point, that is root EB by 2, and it was your phi 1t. But in the 2-3 previous slides we have seen that it was 2-dimensional message point. So, I have one phi 1t and another one is phi 2t space, and I got S11 is root EB 0, this one is the root EB and 0, and next point was 0 root EB. This is the point 2, okay, point S2, and this is the point S1, and this is your decision boundary. If I will get any point at this point, in this point, then I will consider as S1, okay. If I will get any point in this region, then I will consider that point as a S2, okay. So region Z1 is corresponding to meshes S1. You can see that region Z1 is corresponding to meshes S1, and Z2 is corresponding to meshes S2. So the distance between two meshes points is given by, so I can find out the distance, okay. I can find out this distance from basic coordinate system. I can find out this one is your root EB square, that is your 2 points are there, 0 root EB, and this is your root EB and 0. How I can get this distance? Root over of this point, I can let us say x1, x2, y1, y2. So I can write y1 minus x1 root over square plus y2 minus x2 root over square. So root EB minus 0 whole square plus 0 minus root EB whole square. I will get this root EB square plus root EB square, that is nothing but your root 2 EB. This is your basic BFSK transmitter. So in case of ASK, it was only this this was the M of t and some phi 1 t, but in case of the BFSK transmitter, we have two basis functions, that is cos 2 pi f1 t and cos 2 pi f2 t. So our message signal binary wave is going in the form M of t, and another is inverted M of t, that is M bar t, and it would be multiplied by phi 1 t, and in the first product modulator, this is product modulator, and this one the second product modulator, and it would be multiplied by phi 2 t, and then it would be added or summed at the end point, and I will get the binary FSK waveform, okay. So after receiving the binary FSK signal, this is your binary FSK signal, I will pass through one again one product modulator, that is for synchronous detection. I will use again same carrier, and in the similarly in the second product modulator I will use the phi 2 t, and I will pass these two product modulator output signals to a integrator, okay. So after integrating this, that x of t is assembled of x1 t and x2 t, and after integrating this I will get only x1, and here I will get only x2 t, and I will add this signal at the adder, and I will get the main output as L. So I will now, after getting the L, if I am sending 0, whether I am getting 0 or 1, it is depends on the decision device, okay. The decision device, it will choose 1 if L is greater than 0, if it will choose 0 if L is less than 0. This is the decision device condition. So your how can I find the x1? So x1, how can I find x1? That is integration of 0 to tb. Incoming signal is this is the incoming signal, that is x of t multiplied by phi t, x of t multiplied by phi t. Here your signal is your x of t multiplied by phi 1 of t, and that would be integrated in the integration device, that is 0 to tb dt, okay. This is the 0 to tb x of t phi 1 t dt, and next your x2 t, sorry x2 only, for same fashion using same fashion x1 t, I will get x2 t as x2 of t is 0 to tb x of t multiplied by your same x of t is going product modulator 1 and product modulator 2. So, your x of t is same, and instead of phi 1 t I will use phi 2 t dt. So, where x of t is the received signals, okay, that x of t is your received signal. So, I will now, till now we have transmitted the signal and we got the signal what is the x1 and x2. Now, I will find whether I am getting correct signal or not, and that is why I have to analyze some error performance. So, in case of BASK also we have analyzed the error performance. So, here is also we will analyze the performance of error performance of BFSK, binary FSK. So, when symbol 1 is transmitted, your x of t equal to nothing but your S1 t plus some noise. We have already seen in ASK also that in the noise environment we are sending the signal. So, that is why noise is added at the receiver. When symbol 0 is transmitted, x of t equal to S2 t plus W of t. So, now I can define one random variable, that is L, which is Gaussian in nature, whose sample value is L, which is nothing but the difference between your x1 and x2. So, here I have differentiated this x1 and x2, and I have taken this as small l. The mean value of L depends on which binary symbol was transmitted. Okay, the mean value will depend on the symbol which we have transmitted. So, the conditional mean of the random variable L under the condition that symbol 1 is transmitted is given by. So, if this is the conditional mean, there I have sent the symbol 1 is transmitted. So, this is the given, that is 1 is transmitted. What is the mean of the L? That is the E of nothing but the x1 given L minus, this is the, actually this L is belongs to capital L. So, L I can write E of x1 L minus E of x2, because this is x1 minus x2. So, expectation of x1 given 1 minus expectation of x2 given 1. So, I can say that expectation of x1, what is the expectation of x1 if I have sent 1, that is nothing but your root EB, and what is the expectation of x2 if I have sent 1, it is your 0. What is the value of x2? That is your 0, that is why this difference is your root EB. Similarly, the conditional mean of random variable L under the condition that symbol 0 is transmitted. Before that we have seen symbol 1 was transmitted, and now it was symbol 0 is transmitted. So, E of L0 symbol 0 is transmitted. What is the expectation of L? That is x1 minus x2, same x1 given 0, x2 given 0, that is nothing but this is 0 is transmitted, and this is what is the value of x1, that is your, this is your 0, and what is the value of expectation of x2 when 0 is transmitted, that is your root EB. So, 0 minus EB nothing but your minus root EB. Okay. So, similarly, variance of random variable L is given by, variance is nothing but your, in both cases it is variance of x1 plus variance of x2, because variance is always added. So, variance of x1 is nothing but your n naught by 2. Similarly, variance of x2 is nothing but your n naught by 2. So, this is nothing but the n naught. Okay. When symbol 0 was transmitted, then the conditional value of the conditional PDF of the random variable L is given by, because we know that the PDF of the Gaussian random variable this is, and the conditional PDF, that is f L of L given 0 is nothing but 1 by root 2 pi, this is your sigma square. Sigma square is nothing but your, now we have got the sigma variance of capital L, that is your n naught. So, variance is your now n naught. So, I have put this n naught. Then exponential of your x is nothing but your small x is nothing but your what? Small h is nothing but your small l, that is small l, minus mu. Mu is nothing but your mu, that is your mean. mean is nothing but your minus root EB. Okay. So, this is L minus root EB. So, it would be L plus root EB whole square divided to sigma square. Sigma square is nothing but your N naught by sigma square is nothing but your N naught only. Okay. So, your 2 N naught. Okay. So, assume symbol 0 is transmitted, but at the receiver I am getting x1 is greater than x2 or L is greater than 0, that is I am getting 1. Thus, the receiver makes the decision in favor of symbol 1. Okay. If I am sending 0, I will the receiver is making a decision as a symbol 1. Therefore, the probability of error corresponding to symbol 0 is given by probability of 0 equal to nothing but probability of L greater than 0. What is the probability of getting L equal to greater than 0, but given symbol 0 was sent. So, I can get the what I will do integrate the L greater than 0 PDF DL. So, I know what is the f of L greater given 0, this is the PDF. This is 1 by 2 pi n naught root integrate 0 to infinite exponential of this much. So, let L plus root EB by 2 n naught root 2 n naught equal to 0. Now, I will get DL equal to root 2 n naught dz, and I can get the PE of 0 equal to 1 by root pi multiplied by your exponential of minus z square. I will put this is a minus z square. Instead of DL, I will get DL. I will get root 2 n naught dz, and here you have root 2 n naught here also. So, here also root 2 n naught, it will cancel out, and I will get the for infinite I will get infinite, and for 0 I will get the, if I will get it would be 0, it will I will get root EB by 2 n naught as a lower limit. Okay. So, P of naught equal to half, I know the form, that half ERFC of root EB by 2 n naught. Okay. So, similarly, the probability of error corresponding to symbol 1 is given by P of 1 equal to half ERFC of root EB by 2 n naught. So, the average P for coherent binary FSK is P equal to half P naught plus half PE1, that is equal nothing but the half ERFC of root EB by 2 n naught, but in case of ASK it was half ERFC of root EB by 4 n naught. So, it is the we can see that this is the PE expression, and it was the PE expression of a binary ASK, or I can write like this. So, this is the FSK system, and we have seen the what is the we have analyzed the BASK BFSK transmitter and BFSK receiver, and then we have calculated the bit error, that is probability of error when 0 is transmitting, but I am getting 1 at the receiver, and I am sending 1, but I am receiving 0 at the receiver. So, these are the basic calculations or analysis. So, these are the books you can read, these are the standard books only. So, thank you very much. In the next class, we will see the another modulation scheme, that is binary phase shift keying. Okay, thank you.